Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. Welcome back in class of elementary number theory by David and Burton. From last two lectures, we are discussing about the pseudoprimes. I hope you have seen that lectures. In today's lecture, we will discuss one of the most important pseudoprime, that is Carmichael number, after the name of American mathematician. R.D. Carmichael, Robert Daniel Carmichael. He was an American mathematician. He found the Carmichael number. What is Carmichael number actually? In last lecture, you have seen that there exist some integer which are pseudoprimes with respect to some base, but for other base that is not a pseudoprime. For example, 85 is a pseudoprime for base 2, but not base. 85 is a pseudoprime for base 4, but not for base 2. So, if a composite integer that is a pseudoprime for every base, then that pseudoprime is called a Carmichael number. And this is the virtue, this is the quality of a pseudoprime. So, how can we define Carmichael number? A composite integer n that is a pseudoprime for all bases a greater than or equal to 2 is called Carmichael number. In other words, n is called Carmichael number if it satisfies a raised to power n minus 1 congruent to 1 modulo n for all a greater than or equal to 2 such that a and n both are relatively prime, mean to say their GCD is 1. So this is the definition of Carmichael number. Next, we show that the first Carmichael number is 561. We have to show that 561 is a pseudoprime for any base. In last lecture, I show 561 is a pseudoprime for base 2. Today, we will show that 561 is a pseudoprime for any base. If you take base 3, base 5, base 4, it will always a pseudoprime. Show that n is equal to 561 is a Carmichael number, and this is the first number. To show this is a Carmichael number, firstly we have to choose a base, any arbitrary base. Let a greater than or equal to 2 be any base for n is equal to 561 such that this base a and this number n 561, this is always co-prime. Next, to show that some number is a co-prime, some number is a pseudoprime, we have to make its prime factorization. The prime factorization of n is equal to 561 is 3 into 11 into 17. So when you say 561 is relatively prime with a, it means the GCD of a with its first prime factor, that is 3, will also equal to 1, because 3 is a part of 561, is a factor of 361. That's why its GCD with A will always also equal to 1. Similarly, GCD of A with 11, this is also equal to 1. GCD of A with 17, this is also equal to 1. Now I will use Fermat theorem for all of these prime factors 3, 11, 17. What is Fermat theorem? The Fermat theorem says if P is any prime and A is any integer either positive, negative or 0 such that the A and P are co-prime, then they satisfy A raised to power P minus 1 congruent to 1 modulo prime P. So we will use Fermat theorem separately for all of these prime. So when you take the first prime P is equal to 3, we will not choose any specific base A, like as in our first lecture we take A is equal to 2. In the second lecture I discussed we can take A is equal to 4, because we have to show that 561 is the Carmichael number for any base. So we will not replace A with any number. So when you put P is equal to 3 here with base A that is greater than or equal to 2, this becomes A square. This is congruent to 1 modulo, what is modulo? The first prime, this is 3. Similarly, when you choose the second prime number, that is 11, then again by using Fermat theorem, this becomes A raised to power 10. This is congruent to 1 modulo 11. Say this is 2. Lastly, put here the third prime number, that is 17. This becomes A raised to power 16 congruent to 1 modulo 17. Say this is 3 here. I have to show that n is equal to 561 is a pseudoprime for any base. So for this I will show that A raised to power 560 is congruent to 1 modulo 561. This is my target to show. Okay. I will use all of these three congruences simultaneously, consider one, using one. As A raised to power 560, that is the left side of this congruence, this can be written as A raised to power 2, as 560 is completely divisible by 2, so this is equal to 280. We can write it here 280, and this is congruent to 1 modulo, what is my modulo is 3 here. In 3, A square is congruent to 1. When you divide 560 by 2, this gives the quotient 280, so we can separate 560 as 2 into 280. A square is congruent to 1, this becomes 1 whole power 280, but 1 whole power 280 is equal to 1, so this is congruent to 1 modulo 3. This shows A raised to power 560 is congruent to 1 modulo 3 here. Similarly, when you use the second congruence, that is A raised to power 10, A raised to power 560 is again can be written as A raised to power 10 whole power 56, and again this is congruent to 1 by using 2 modulo 11. Lastly, when you use the third congruence, A raised to power 560, and here this is 16. This is equal to A raised to power 16. When we divide 560 with 16, this is equal to 35. Okay. Yes. This is congruent to 1. A raised to power 16 is congruent to 1. So this becomes 1 whole power 35. 1 whole power 35 is 1. This is congruent to 1 modulo 17. Say this is congruence 4, congruence 5, congruence 6. By using all of these congruence 3, 4, 5, 6, A raised to power 560 is congruent to 1 modulo their LCM, modulo the LCM of these moduli. modulo 3 into 11 into 17, this becomes congruent to modulo 561. And this shows our required result. From this example, you can notice that this shows that 561 is a Carmichael number. From this example, you can notice that we have not used or contribute the base A. This just depend on the exponents. 2 into 2 raised to power 80. There is a no utilization of A here. Again, this is the product of 10 into 56. This is the product of 16 into 35. It means a number is a Carmichael if it is completely divisible by the prime factors, or in other words, we can say that this is the Carmichael theorem, which says n is called Carmichael. This is Carmichael theorem. I hope this is the Carmichael theorem. This theorem says n is called Carmichael number if some prime p divides n, then p minus 1 divides n minus 1. N is called Carmichael number if and only if the first, this theorem has two conditions. The first condition is n is the product of, I should write here, this theorem says n is called Carmichael number if and only if the first condition is n is the product of distinct prime factors that is square free. Square free mean like you make the prime factorization of 12. This is equal to 2 square into 3. So this cannot be a Carmichael number because its prime factorization contains square. Similarly, you make the prime factorization of like 250. The prime factorization of 250 is 2 into 5 cube. So 5 cube is also divisible by 5 square. So we can say that this number is also not a square free number. Square free doesn't mean that it just contains square of number. Square free means it should not be divisible by the square of other prime factors. This number is divisible by 5 square, so I can say that this number is not a non-square free numbers. So the first condition is that n is the product of distinct prime factors that is a square free, mean to say it is just product of prime numbers with no power, only power 1, like p1 into p2 into p3 up to some pk. This is the prime factorization of n. There is a no prime factor that contains some power k, some power k1, k2. This is not the case. The second condition is if some p divides n, this implies n minus 1, this divide p minus 1 divide n minus 1. If some number satisfies these two conditions, then that number will always a Carmichael number for any base. So this is a very interesting result. You can utilize this result in your MCQs based exam. For example, we have to test whether n is equal to, suppose my number is n is equal to 12. Is this number a Carmichael number? No, this is not a Carmichael number, because the prime factorization of 12 is contains square. Is n is equal to 100? 100 is the Carmichael number for any base? No, this will be not a Carmichael number because its prime factorization 2 square into 5 square. Both of the number contain square factor, so n is equal to 100 cannot be a Carmichael number. Suppose my number is n is equal to 35. Is this number a Carmichael or not? The first condition is, what is its prime factorization? This is 5 into 7. The first condition hold. Second condition says, if some prime number divide n, so my first number p is equal to 5. You can notice that 5 divide n, what is n? 35. But 5 minus 1 does not divide 35 minus 1. That is 4 does not divide 34. So second condition does not hold here. This shows n is equal to 35 cannot be a Carmichael number. Similarly, if you take the second prime number p7, then 7 minus 1, this is 6. 6 does not divide 35 minus 1, 34. So this shows that 35 is not a Carmichael number. Similarly, if you take n is equal to 51, this is the product of 17 into 3. The first condition hold, this is the product of two distinct prime factors without containing any power. Now 17 minus 1, this is 16. Is 16 divide 50? No. This shows that 51 cannot be a Carmichael number. So this is the one of the most important trick to check whether a given number is a Carmichael or not. So I hope now you have a clear understanding about Carmichael number. The next Carmichael number is 1105. So this is your assignment. You have to show that 1105 is a Carmichael number. So if you find this lecture helpful, kindly like, share and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.